All right, let's look at example 2, which is a different kind of situation, but it has something in common with example 1, which is that we have different groups of people, different quantities of people, which are changing their amounts depending on the quantities of the other groups. Let's see how that works. So we have a population of 1,000 susceptible people. Maybe this is an island or something, and a new virus emerges because somebody comes in on a boat or something like that. So each day, 8% of the susceptible people become infected. So the more susceptible people there are, the more people that will become infected. And 40% of the infected people recover, and 1% of the recovered population becomes reinfected. So once you're recovered, you have some immunity to it, you're much less likely to get it than if you've never been exposed to it before. So we're going to say that Pn is the number of susceptible people, infected people, and recovered people n days later. Let's first notice that on day 0, we have just 1,000 susceptible people. 0 people currently infected and 0 people that were infected but recovered. So we're starting with that. Now, after 1 day, I guess this virus spreads pretty darn fast. So P1 means after 1 day, what is the number of susceptible people, currently infected people, and recovered people? Well, let's think about what happens to all of the susceptible people. Well, we know 8% of them are going to be infected. So 8% of those 1,000 people are going to be infected. But what about the other 92%? Well, they are still susceptible. And nobody's had a chance to recover yet, so we won't worry about what happened to the previous infected people or recovered people because there were none of them anyways. So anyways, the S0 is 1,000, so this is just going to become 920 and 80 here. So that's P1. Down here, let's find P2. So after 2 days of this virus going around, well, first let's think about the susceptible people from the previous day. There were 920 of them. 92% of them are still susceptible people. 8% of them are currently infected, and nobody can go straight from being susceptible to recovered, so there's going to be a 0 here. Now let's think about what happens to the 80 people who were infected yesterday. Well, nobody can go straight from being infected to susceptible, so I could maybe write a 0 I1 here. We do know that 40% of the infected people recover. So the number of recovered people the next day is going to include this 40% of the infected people. And what about the other 60%? They're still infected on day 2. And then let's think about the recovered people. Well, there were no recovered people, so we know this is going to be 0, but let's think about it anyways. We know that 1% of the recovered people can become reinfected. So we could think of that as 0.01 times recovered people, and then the other 99% of people that are recovered stay recovered, but you can't go from being recovered to being susceptible again. So with the numbers we had previously, this is just going to be so this all works out to be 846.4 susceptible people, 121.6 infected people, and 32 recovered people. Okay, P3 is going to be the same idea. Now we know the same thing is going to happen. We're still going to get 92% of the previous day's susceptible people, are still susceptible, 8% become infected. And so how can we think of this as a matrix that we multiply by the vector S2, I2, and R2 is the goal? Well, it looks like we're doing a linear combination of these three vectors here. We're doing S2 times the vector 0.92, comma 0.08, comma 0, right? And then we're doing I2 times 0, 0.6, and 0.4. And then the recovered people, we have 0, 0.01, and 0.99. So it sounds like this is our A that we're going to multiply by P2 to get P3. All right, so I already typed in the A and the P0 here, so we can ask the computer to do A times P0. That is the same P1 we got earlier. And then we can do A times that to get P2, which is the same thing we got when we did that by hand earlier. And now we want to do A times this to get P3. So we get that as the P3. Now, of course, we could have also just written that as A to the power 3 and then that times P0. Exactly the same thing. So yeah, we did find the A that makes it so in general P sub n plus 1 is equal to A times P sub n. Like we saw before, we could also write this in the form P sub n in general is equal to A to the power n times P0. So that makes it so we can see what happens in the long run. Now, fortunately, with this virus, it doesn't look like anybody's dying from it. In fact, it doesn't look like anybody's dying at all on this island. Nobody's being born either. Everybody's just moving between these three groups of susceptible, infected, or recovered. So at every point, the total number of each group should add up to 1,000. But let's see what happens if we do like A to the power 30 times P0. So after 30 days, at this point, it still looks like it adds up to 1,000. The biggest group of people here is now recovered, which is good. But are there always going to be some susceptible people, or is eventually everybody going to be infected? And are there always going to be some infected people, or is everybody eventually going to recover? How will it work out? Let's see. Let's see what happens if we do a really big number, like 300 days later. All right, so this is 1.36 times 10 to the power negative 8. So that's actually 0. So there's now basically 0 people susceptible. There's still 24 people infected, but most everybody's recovered. So is it always going to be about 975 people recovered and 24 people infected? Let's see what happens after some more days, like maybe 1,000 days later. It's about the same. Interesting. So it seems like the limit as the number of days approaches infinity of P sub n, it's going to be approximately 0, 24.4, and 975.6. Now maybe that kind of makes sense that there's going to be this equilibrium where a percentage of the recovered people, 1% of the recovered people are always getting reinfected, and then some of them are becoming recovered again. And this is like a point where it all balances out. Now, like I said, when we get to eigenvectors and eigenvalues, we are going to see how to like calculate these numbers just based on the matrix. Now, before we get to diagonalizability, I just want to point out a few things here that this example is different from the previous one where each column of A adds up to 1 because what is happening here is the population is not growing or shrinking. This description is telling you essentially what happens to 100% of the susceptible people, what happens to 100% of the infected people, and what happens to 100% of the recovered people, which is why all of these columns of this matrix add up to 1. So this is a special kind of matrix when you have that situation. You call it a stochastic matrix. It's really important in probability theory and statistics. It's useful for modeling a lot of complicated real-life things like this. Now, in the real world, it's not actually going to be exactly 8% every day, right? Like it depends on what's going on that day. Some days it might be 15% of the susceptible people become infected, and some days it might be 1% of the susceptible people become infected. So there's a lot of randomness in the world, and you model those with what's called Markov chains. That gets a bit more complicated than what we're doing here because you would have like a probability density function instead of just like the number 8%. And it gets a little bit more complicated, but this is sort of like the foundation of that. So yeah, it turns out when you calculate a to the power n in a lot of real world calculations, the matrix might be really enormous. Like if you're doing an ecological example, you might have thousands of species in the ecosystems whose population affect each other in various ways. And Google's PageRank algorithm uses powers of a square matrix with a row and column for every page on the web, and there's a whole lot of those. So this can get out of hand really fast. Like we could see just by like doing this by hand once, it takes a little bit of work. But if you had a like 1 billion by 1 billion matrix, and then you wanted to calculate a to the power 1000 or something, that's getting into territory where a computer can't really do that without some kind of help. And diagonalization is going to make this calculation much easier and also help us understand what's really going on when we talk about powers of a matrix like this. So we'll see that in the next video.